So, students, we talked about the concept of probability in the previous session. In this session, I am going to concentrate on probability distributions. Like frequency distribution, you are aware of. Frequency distribution show frequencies against values of variables in a tabular form or a graphical form. In the same way, we have probability distributions, which show probabilities of a random variable or a probability variable taking certain values. The variable may be discrete. Discrete variables are those which take fixed values in a given range, like age in completed years is a discrete variable. Completed years means somebody can be of age 15, 16, 17 and cannot be of age 15.5. Continuous variables are those which can take any value in a given range, and accordingly we have discrete and continuous distributions also. Discrete distributions are those which describe the random behavior of discrete variables, and continuous variables are those which describe random behavior of continuous variables. The most used of all the distributions in a social science is a normal distribution, which is a form of continuous distribution. Now, behind the idea of probability distribution is the concept of probability density function. Probability density function is a mathematical expression which expresses the probability of a random variable acquiring a specific value if discrete, or any value within a given range if continuous, and it is shown as follows: f x if discrete, f x dx if continuous, because f x means probability that a random variable x takes a value x, while f x dx shows the area under the probability density function between two values x and x plus dx. For continuous variables, we cannot define probabilities for specific or exact points, we define probabilities for a given range, and the range is very small, dx is very small. As this as in the earlier lecture, we defined in the term infinity as very large number, the dx is a very small interval. f x dx therefore refers to an area between x and x plus dx. This f x contains one or more constants when expressed in a mathematical form. Suppose I say that f x equal to a plus b x, then a and b are two constants, they can be called the parameters of the distribution. F x obviously takes different shapes depending on the values of the parameter or parameters a and a plus b x for different values of a plus b, a and b, a plus b x will have different forms. Likewise, probability density functions take different forms depending on the values of the parameter. Normal distribution you must have heard about, or which is commonly used, has two parameters, mean mu and standard deviation sigma. Depending on the values of mu and sigma, normal distribution takes different shapes. For various values of constants, f x may be called therefore a family of distribution, like normal distribution. This is the density function of a normal distribution. Actually, in a general form 1 upon sigma root 2 pi e raised power minus half x minus mu by sigma square, you are referring to a family of distribution. It is family, it has several members, because for specific values of mu and sigma, the shape, the range, etc. of normal distributions will be different. Every density function with a given value of a parameter is a member of these families of distributions. All algebraic functions are possible, such as kx, k into e raised power cx, or k upon x, or k log x, or Ka plus Bx or e raised to power minus lambda, lambda raised to power x by all mathematical expressions can be thought of as probability density functions if they meet certain conditions. What are these conditions? That the value of x is in a given range, and in that range the value of f x lies between 0 and 1, because f x is a probability that a random variable x takes a value x. So, f x cannot go beyond 1 and it cannot be a negative number, 0 and 1. These are the limits of f x, because probability cannot be negative or more than 1. And sum of all the probabilities for all values of x, x always has a range, and if you add up probabilities of x for all possible values in this range, then you should get 1. That means sigma f x for continuous, sigma f x for discrete variables and integral f x dx for continuous variable should be 1. So, we have a mathematical law, a probability distribution may be seen as a mathematical law that describes the behavior of a random or stochastic variable. The randomness may be caused by the sampling fluctuations in case of sampling theory, measurement errors which is always unknown, and often in statistics we assume that error follows a certain distribution with certain mean and variance. Unknown determinants of a dependent variable in a model, in regression model, bivariate or multivariate. If all the determinants of the dependent variable are not included in the model, then you have more error, and then error follows a distribution. Or the nature of behavior of the object, as in quantum physics. In quantum physics you cannot specify simultaneously the position and momentum of a particle, that is also a kind of randomness. Population of India, suppose we want to project population of India in 2050, this is uncertain. Nobody can exactly predict what will be India's population in year 2050, but based on available projections one may say that there is a high probability, say 0.60, that it is 1.6 billion, that in 2050 India's population would be 1.6 billion, and we can say that the probability of its being 1.6 billion is 0.60. There is some probability, say 0.20, that it will be 1.4 billion, and there is also some probability 0.20 that it will be 1.8 billion. We can make such a statement. We can make a better statement about population projections of India, but this can be one simple statement. This is an example of discrete probability distribution, where f x for x equal to 1.4, 1.6 and 1.8 is such that f 1.4 equal to 0.20, f 1.6 equal to 0.60 and f 1.8 equal to 0.20. This can be shown through a line diagram or an algebraic function which will be called probability density function. In algebraic form I can write f x equal to 0.60 x minus 0.6 square for x equal to 1.6 and f x equal to 5 times x minus 0.6 square for other values of x. So, this is an example of how probability density function can be formed. Is it not better to look for a continuous distribution? Just here we are saying that population of India in 2050 can take only 3 values, but it is not a reasonable assumption. It may take a value 1.6, it may take 1.5, it may take a value 1.4 or 1.3, or above 1.6 it may be 1.7, 1.8, 1.81, 1.83 or any value. So, it is better to make projections treating population as a continuous variable, and one may say that there is a probability 0.60 that it is above 1.7 billion, and there is a probability 0.40 that it will be less than 1.7 billion. We may refer to a normal distribution in which 1.7 is a point below which 40% area lies. If a normal distribution fits the projections of India's population in 2050, we can convert this statement that probability below 1.7 is 0.6 and that the probability above 1.7 billion is 0.6 and probability below 1.7 is 0.4. This can be stated in the form of a graph of a normal distribution. Let the population in 2050 follow a normal distribution with mean 1.8 billion and variance 0.57. Now, this is the density function of a normal distribution. It is symmetrical, its mean, median, mode lie at the same place, and the probability that the value of random variable z is less than say z1 is this area, and the probability that it is more than this is this area. For z1 equal to minus 0.25, we can write, if the value of the normal variate is 1.7, then we can write z as standardized value minus 0.25 equal to 1.7 minus mu divided by sigma. Mu is the mean of the distribution and sigma is the standard deviation. If we know mu or sigma, the other value can be estimated. From this formula, if we know mu or sigma, any one of them, then the other value can be estimated. So, if you assume some value of the later, means sigma, you may estimate the most likely value of the former. Now, let us apply this to our population projection example. Let us assume that the most likely projection mu means most likely value, modal value, mean, median. The most likely projection is 1.8 billion and the sigma is 0.4. We can say that we are 95% sure that in 2050 the population of India will lie between 1.8, which is mean or most likely projection, minus 1.96 multiplied by 0.4, and 1.8 plus 1.96 multiplied by 0.4, that is between 1.016 and 2.584. It is an interesting thing. If we know the probability density function of a variable and some property, then we can predict confidence intervals. We can say we are 95% sure. Now, population being a random variable, we can only state its behavior in terms of certain probabilities. We can say that we are confident that it will be around 1.8, but in addition to that, in case of probabilistic variable, we can also say that we are 95% sure that this value, if it differs from 1.8, it can differ from 1.8, but it will be definitely in a given range of 1.016 and 2.584. What I assume that the most likely projection mu is 1.8 and SD sigma of the distribution is 0.4. If sigma is something else, then the confidence interval will also change. Such statements are called confidence intervals. You can make 95% confidence interval, you can make 99% confidence interval, 99.9%. In management literature or in management departments, 6 sigma is very famous for a measure of accuracy, which derives from the fact that in 99% cases the values must lie within the range of 3 sigma on either side of the mean. Such statements are called confidence intervals. Okay. They cannot be made with deterministic models. If you use deterministic models, then you can only say that like you can use a linear model or exponential model or Gompard's model and predict population of India for 2050, but that will be a point prediction. You can only say that my projection is this, my prediction is this, but you cannot give a confidence interval. The advantage of probability distributions is that you can also specify a confidence interval. The width of interval depends on sigma, standard deviation, and the degree of confidence interval required, this 95, 99, 99.9. A simple example of PDF. To explain the concept of PDF, let me give a simple example again. If fx equal to x for x equal to 3, 5 and 6, can it be called a probability distribution? Fx equal to x for x equal to 3, 5 and 6. This means f3 is 3, f5 is 5, f6 is 6. The answer is no, because all f values are greater than 1. To be probability density function, these algebraic functions must be such that every value of fx lies between 0 and 1. So, when f3 is 3, it cannot be indicating a probability density function, because fx should not be more than 1. What about fx equal to x by root 7 for x equal to 3, 5 and 6? Again, this is no probability density function, although now all the values of fx are less than 1. X upon 7 means 3 by 7, 5 by 7, 6 by 7, all the values are less than 1, but it is still not a probability density function, because sum of f3, f5 and f6 equal to 3 by 7 plus 5 by 7 plus 6 by 7 equal to 14 by 7 equal to 2. Sum of fx should not exceed 1. So, this is also not a probability density function, although all fx values are less than 1. So, fx equal to x by 7 is rejected as a probability density function. For the same range, fx equal to x by 14 can however be called a probability distribution. How? The three values for x equal to 3, x equal to 5 and x equal to 6, the values of fx would be 3 by 14, 5 by 14 and 6 by 14, all are less than 1, and if you add them up all, then you get 3 plus 5 plus 6, 14, 14 by 14 means 1. So, this fx equal to x by 14 for 3 specific discrete points of x, 3, 5 and 6 can be called a probability distribution. It is discrete and it can be shown like this. The probability, these are for 3 the probability is this, for 5 probability is this, for 7 probability is this, and it is a linear function. Okay. For 3, 5 and 7, these are the probabilities, fx equal to x by 14. So, in mathematical terms you can write fx equal to x by 14, and graphically you can show it like this. The line ends here, the line starts here. In continuous distribution, probability is shown by area. For example, here is a picture of a normal distribution, and the mean of the distribution is at 180. Standard deviation of the distribution is 10, and you can say that the probability that such a random variable which has mean 180, standard deviation 10 and follows a normal distribution, the probability that this variable can take a value in the range 160 to 170 is this area, and this area under the distribution is 0.135905. This means if you have multiple experiments, then in 0.35 135 means in 13.59% cases the value of this random variable will lie between 160 and 170. If a variable is random and follows a normal probability distribution, then theoretically it can take any value from minus infinity to plus infinity, but normal distributions, because 99% values lie within plus minus 3 sigma, and sigma is a finite quantity 10. So, between mean plus and minus 30, 99% values lie. Practically normal distribution can be used even when the theoretical limits are not minus infinity and plus infinity, but they are finite. And in normal distribution we cannot say what is the probability that the variable will take a value 160. No, it cannot take, we cannot specify probability of the variable taking a value 160. We can only say that probability that the variable takes a value between 160 and 170, a range. In continuous distribution we specify a range, and the probability of variable lying in this range is 0.135905. That means, in 13.59% cases the variable will take values in this range. Some common distributions which have been used in social sciences or sociological literature are rectangular or uniform distribution, binomial distribution, Poisson distribution, negative exponential distribution, normal distribution, T distribution and F distribution. Rectangular distribution. Rectangular distribution can be specified for a discrete variable or for a continuous variable. The meaning is that in case of discrete variables, probabilities that a variable takes this and this, any of these values is same, that is rectangular distribution. These are empirical data of certain experiment, and here the heights of bars shown at different places are not exactly same, but they are similar. So, one can assume that for this kind of empirical or distribution or data, a rectangular distribution will fit better. For a continuous distribution, if values of x lie between a and b, then f x dx equal to 1 upon b minus a dx will be a rectangular distribution. All f x dx values are less than 1, and integral f x dx from a to b would be 1. So, this meets the conditions of probability distribution. Binomial distribution. Binomial distribution is defined algebraically as f x equal to n c x p x 1 minus p raised to power n minus x. When the trials are independent and you want to know how many times out of n trials a particular event or success occurs. For example, getting 5 heads, if a coin is tossed 12 times, if a coin is tossed, then we may assume that if coin is unbiased, then the probability P, probability of occurrence of some event, events are only 2, head and tail. So, probability of head is P 0.5, probability of tail is 1 minus 0.5, again 0.5. The probability that out of 12 experiments of tossing this kind of coin, 5 heads will occur, will be 12, 12 C 5, 0.5 raised to power 5 and 1 minus 0.5 raised to power 12 minus 5, because 12 minus 5 means 7 tails and x equal to 5, 5 heads. 5 heads, 7 tails, probabilities are 0.5 and 0.5. P and 1 minus P need not be same always. If the coin is not unbiased, it is biased and P is 0.7, then 1 minus P will be 0.3. This is an example of binomial distribution. Binomial distribution, in any situation in which there are only two possible outcomes with probabilities p and 1 minus p, then you can apply binomial distribution. There is another distribution called Poisson distribution. In Poisson distribution, algebraically f x equal to e raised power minus lambda, lambda raised power x, factorial x. Lambda is a constant and it is called the parameter of the distribution. The value of x may be anything between 0 and infinity. When n is very large and the probability of occurrence of an event is very small, so that n multiplied by p is a small number, a finite quantity. For example, number of arrivals in a queue for some service, then we use Poisson distribution. Negative exponential algebraic expression is f x dx equal to lambda e raised power minus lambda x dx for values of x, any value from 0 to infinity. For example, waiting time in a queue or birth interval. Waiting times in queue for any service or birth interval means time between two consecutive births, they are known to follow negative exponential distribution. This is your standard normal distribution and I suppose you are familiar with this. This is f x equal to 1 upon sigma root 2 pi e raised power minus half x minus mu by sigma whole square. X lies between minus infinity and plus infinity. It is suited for large samples, for example, distribution of mass in a large class. A small class, if you have 5 students in a class, their mass may not be normally distributed, but if you have a large class, I have always found that in a large class means in a class of 100 or more students, if you plot the distribution of number of students against marks may be classified into groups, like out of 100 marks it can be 0 to 10, 10 to 20, 20 to 30 etc. Then you find a neat symmetrical distribution. Most of the times in statistics there is a rule, the law of large numbers. There is also a central limit theorem which says that things which consist of sum of a number of random variables follow a normal distribution irrespective of the distributions of specific variables. Binomial now in the beginning I said that probability density functions are actually specifying a family of distribution. They are not just one distribution. So, NCX, PX, 1 minus P, n minus x, this is a family of distribution and the shape of the distribution will depend on the values of P and n. So, here is an example. Here you have binomial distribution. In these this first blue color distribution is shown for n equal to 5, p equal to 0.5. Because p is 0.5, it is a symmetrical distribution. If p is not 0.5, it will become asymmetrical or skewed distribution. In the language of statistics, I can say skewed distribution. For n equal to 5 and p equal to say 0.4 or 0.6 or 0.7, it will be a skewed distribution. These bar diagram for different values of x, these probabilities are given in the forms of bars, and this diagram is for a binomial distribution in which n is 20. Total number of trials or experiments or observations is 20 and probability of occurrence of some event is again 0.5. That is why it is also a symmetrical thing. If you change p from 0.5 to something else, then it will become asymmetrical. It can be a sort of negatively skewed or it can be positively skewed. This random variable has a binomial distribution again, but n is 50 and p is same 0.5. Now, what has happened when n is 50, the spread of the distribution has increased, heights have changed. So, it is not one, and this binomial distribution is not one distribution, these are examples of families of binomial distribution. These three binomial distributions have the same constant p equal to 0.5, and still they are different. Their modes are different, their heights are different, peak height is different, their variances are different, they look different. So, they are different members of the a broad family called binomial distribution. Similarly, see the behavior of Poisson distribution for different values of lambda. In Poisson distribution, you have only one unknown parameter, and that is lambda. Lambda, here we show three different, this is red is 1, this is for lambda equal to 1, this green one, this is a Poisson distribution for lambda equal to 4, and this is a Poisson distribution for lambda equal to 10. Their shapes are different, their means, modes, medians are different, and one interesting thing you note that as lambda increases, the behavior of the Poisson distribution tends to become normalized. This is negative exponential distribution with different values of parameters. For lambda equal to 0.5, this is for lambda equal to 0.5. They all belong to family of negative exponential distribution. They start from a modal point which is 0 and then decline. The rate at which values of negative exponential distribution decline depends on the value of lambda. So, here the decline is relatively slower when lambda is 0.5, when lambda is 1 it is more, and the decline in the values of x or fx, decline in the values of fx or probabilities is highest when lambda is higher 1.5, and then they become asymptotic. The total area under a binomial or negative binomial, all distributions, in this case negative exponential distribution is always 1. This area below this yellow thing is 1, area under red distribution is 1, area under blue distribution is also 1. This is an example of normal distribution with different values of parameters. There are in normal distribution, when I wrote the algebraic function of a normal distribution, there are two parameters, mu and sigma. Now, look at the behavior of normal distribution when mu's and sigmas differ. For mu equal to 0 and sigma square equal to 0.2, you have this blue kind of this norm. This is the normal distribution for mu equal to 0, mean, mode, median is 0 and sigma square is 0.2. Raise the sigma square, raise it from 0.2 to 1.0 and you are here, this red, this spread has increased because variance is more, mean, mode, median have not changed. Then you raise sigma square further and you have this normal distribution which is becoming more flat, greater spread, mean, mode, median have not changed because mean, mode, median are mu. Now, you change the mu also, mu equal to -2 and sigma square is 0.5. So, then you have this green distribution, this. Here the position of mean, mode, median has also changed. Now, it is -2, mean, mode, median is here at -2 and the spread is shown by sigma square equal to 0.5. So, the point is that all the distribution functions are families of distribution. They are not one distribution, and their actual behavior depends on the values of the parameter. A comment on standard normal distribution. Now, if a normal distribution is a family of distribution, then for actual application, which tables of normal distributions will you consult? If you have used normal distribution at graduate level, BA level, or maybe for your research project, you must have used a table of normal distribution, but that table of normal distribution is unique. So, why is it that or how is it that you can make use of a unique table of normal distribution, while normal distribution is a family of distribution? That is because the table that is given in the books or the table which you can obtain from computers is a table for a specific member of normal distribution, and that member has mu equal to 0 and sigma square equal to 1. So, tables are made for this, and for using any other variable you have to use tables of standard normal variable by calculating z equal to x minus mu upon sigma, and later on you can change z to x again by using x equal to mu plus sigma z. So, when you change when you calculate x minus mu upon sigma, means you change x to z, then it is called standardization of variable. And after consulting the normal distribution table, when you want to come back to x again, then you use x equal to mu plus sigma z. Probability density function of a standardized normal variable, this is any variable x, and when x minus mu upon sigma is replaced by z, then the shape of standardized distribution is this, and the tables that are prepared in the name of normal distribution are the tables of this distribution. The shape of standard normal distribution is this. So, you can find out what is the area between 0 and 0.5, 0 and 1, 0 and 1.5, or 1 to 1.5, between 1 and 1.5, 9.2% area lies, and since normal distribution is a symmetrical distribution, so between -1 and -1.5 also 9.2% area lies, same this area and this area is same. Above 3 only 0.1% area lies, below 0.3 also 0.1% area lies. So, 0.1 and 0.1, 0.2, that means 99.8% area lies between -3 and +3. This is the meaning of 6 sigma. Sometimes you may need to use ordinates of the distribution or heights. Ordinate means height, and for a normal distribution with mean 0, these are the heights. Like at the highest point is at z equal to 0, and it is y equal to 0.3989. The maximum, it is like modal probability, or the maximum probability in a given range is 0.3989, and it is when the normal variable is close to mean. Okay. So, this graph further clarifies the conversion of a normal distribution to standard normal distribution. This is a normal distribution where mean is 1010. By using x minus mu by sigma, this has been converted to this form, shape has not changed. By using z equal to x minus mu by sigma, we reduce this normal distribution which takes values like 950, 970, 990 up to 1070 and still more possible values to values from -3 to +3. Like frequency probability distributions have mean, you can calculate mean of the probability distribution, it is called expected value. To calculate arithmetic mean in a frequency distribution, you calculate sigma fx by n, and here in probability distribution f is replaced by f upon n. So, it becomes sigma px. Mode concept is same, median that divides the distribution into two equal parts, and probability distributions can also be skewed or symmetrical, more peaked than a normal distribution, less peaked than a normal distribution, and you can also calculate higher order moments if need arises, as we have discussed in the lecture on analysis of univariate variables. Just to illustrate, in rectangular distribution mean is at the center a plus b by 2. In binomial distribution mean is np and variance is npq, np into 1 minus p or npq. I am showing this slide to convey that by looking at mean and variance or mean and standard deviation of a distribution, also you can guess what kind of distribution it could be. So, if the mean is at the center a plus b by 2 in rectangular, it can be a rectangular distribution if probabilities are similar and the mean is at the center. A distribution can be a binomial distribution if mean is np and variance is npq, which is less than mean. If variance is less than mean, then it can be a binomial distribution. In Poisson distribution, mean and variance are same. So, if your mean and variance of empirical data are same, you better fit a Poisson distribution, not a binomial distribution. And in normal distribution, mean and variance have no relationship. These are two independent parameters, two different parameters. So, for all possible values of mean and variance, normal distribution can be used, and it is called a two parameter family of distributions. In negative exponential distribution, mean is at 1 upon lambda and variance is 1 upon lambda square. Therefore, as mean decreases, the variance also decreases. So, these are some hints to decide which distribution may fit my empirical data. Again, a simple example, let the random variable be grade in a large course having values 0, 1, 2, 100, and let the teacher give only 4 grades A, B, C, D to equal number of students. Let A, B, C, D mean grade point of 10, 8, 6 and 4. This results into a rectangular distribution. So, marks are from 0 to 100, grades are A, B, C, D, 4 grades, and the number of students getting A, B, C, D is same 4, 6, 8, 10. Suppose these are the marks 4, 6, 8, 10, and A, B, this 10 is A, 8 is B, 6 is C and 4 is D, and the probability, because A, B, C, D are of same number of students. So, probabilities are 0.25, 0.25, 0.25, 0.25, same probability. This line against 4 marks, 6 marks, 8 marks, 10 marks, actually marks 0 to 100, marks converted into some sort of index 4, 6 or grade 8, 10. Same, this straight line shows that there is same number of students getting A, B, C, D. If you add these probabilities from 4 to 10, then you have 0.25, 0.50, 0.75 and 1, this line, and this is called cumulative probability density function f. While probability is shown by small f x or p x, this cumulative function is shown by capital F. To distinguish between f and p, I have used capital F and p, but you can use f also here, but that will be small f and capital F. If x is a discrete variable and takes values 4, 6, 8 and 10, possible values of small f x go from 0 to 1. In this example, f x is constant 0.25 for all values of x. You can write it as in algebraic form k equal to x raised to power alpha, where k is 0.25 and alpha is 0. All x is raised to 0 will be 1. Capital F x or the distribution function shows a rising function and it goes from 0 to 1. The other values of k and alpha, if you in this function if you take other values of k and alpha, it will not remain a rectangular or equal probability distribution. The shape of the distribution will change. Now, if the class is large and imagine that you take a sample of 2 students from here, the possible value of the average will be 5, 6, 7, 8 and 9. Suppose you are dealing with mean average of some kind, for some purpose you want average marks of 2 students. So, 4, 6, 8, 10, the averages of 2 students from this population would be 5, 6, 7, 8 and 9. The minimum value will be that both of them have 4. So, 4 plus 4 by 2, there should be 4 also, because 4, 5, 6, 7, 8, 9 and 10. The possible values of average would be 4, 5, 6, 7, 8, 9 and 10, because both of them may have 4. So, 4 plus 4 by 2 and both of them may have 10. So, 10 plus 10 by 2 equal to 10, 4, 5, 6, 7, 8, 9 and 10. The number of possible values has increased, and then 4, 5, 6, 7, 8, 9 and 10 they make 8. So, I am sorry, this should not be 1 by 6, this should be, then the probabilities will be 1 by 8, 1 by 8, 1 and like that. There will be some value in the middle which will be higher than this, because the mean value will have greater number of cases. So, the probability of getting a number at the center will be higher than the probability of getting other values, and the shape of the distribution will not remain rectangular. It will become more of a normal kind, and if you take sample of size 3, then it will be more normal than in case of sample of size 2. Probability distribution of average would be normalized kind, and the cumulative distribution will be like this. The shape of both will change. In general, if your sample consists of a large number of students, the distribution of mean is most probably a normal distribution with same mean, but a lesser variance. Mean of the sample mean will be same as of the population from which sample is drawn, and variance will be variance of the population divided by the sample size. So, this variance of the mean will start declining. It will be approximately sigma square by n, and as n increases, n being in the denominator, sigma square by n decreases and the variance decreases. This is of utmost importance in sampling theory. As you increase sample size, you also find that the range, there is something wrong in my calculations here now. 10, earlier the range was 10 minus 4, 6. The range will remain same. 4 plus 4 by 2, minimum value will be 4, maximum value will be 10 plus 10 by 2 or 10. So, range will remain same 10 minus 4, 6. This is wrong, please ignore this. The SD will decline because and the SD will decline because SD of mean will decline because the SD of mean would be sigma by root n. If you increase sample size to 3, the SD of mean will decline further, and increase in sample size decrease fluctuations in mean. We can, fluctuation means standard deviation of mean, and that means the fluctuations in mean decline. This SD of sample mean is called standard error of the mean. So, in empirical works, we begin with empirical data or hard facts, prepare a frequency distribution, identify what mathematical expression will generate this kind of distribution, or what kind of mathematical expression will be close to this kind of empirical graphical expression. According to shape of the frequency distribution, choose a mathematical expression which resembles this. It may be binomial type. First you decide whether your variable is discrete or continuous, and then decide what discrete or continuous distribution you are going to use, and then estimate the parameters. Parameters means unknown constants of the probability distribution by using empirical data. There are several methods for that. We will talk about this in fitting a probability distribution. Then estimate expected frequencies under the theoretical distribution, and finally test. This why do we calculate expected frequencies under the theoretical distribution? Because we want to be sure that we have fitted a right distribution. If the expected frequencies and the theoretical frequency, if the expected frequencies and the empirical data are similar, then we can say that our model fits well. So, this is the whole process of using a mathematical model. Start with empirical data, prepare a frequency distribution, look for a theoretical model which resembles the shape of the frequency distribution, estimate the unknown parameters, and then after fitting the distribution, just check whether right distribution has been fitted or not. Because for all kinds of data, all kinds of distributions can be fitted. Fitted means you have to estimate mean, variance, etc. That can be done, but all distributions will not fit all kinds of empirical data. So, you must check whether your exercise was proper or not, and that is done by estimating frequencies under the model and comparing empirical values with expected values. If the empirical values are empirical frequencies are close to expected frequencies, then the model is called to be fitting the data. And in separate lectures, we will talk about how to fit a model and how to test whether the model fits the data or not. Thank you.